Welcome back. So, I just found some music. Okay, let's go to YouTube again. Open this up. Downloads. I've been taking screenshots from some lectures I've been watching. So this one, we're just gonna go through some stuff. I found all interesting stuff. This lecture.
Just very quickly.
So this lecture, just gonna read my notes. I'm probably gonna have to separate this into multiple episodes. I've been taking notes. I got several pages of interesting things to talk about. So, Earth. We're gonna jump back in kind of with large igneous provinces and oceanic plateaus, really. We were looking over here, so this is in regard to the Earth's expansion process, which plate tectonics is false, just FYI if you don't know that. The Earth expanded from a smaller radius and did so by undercurrents that flowed out in all directions below the crust from the mantle when it was punctured in Pakistan, and then pressure built up until because the current flowed out throughout the globe, it then started to collide and pressure built up, and then it started to create boundaries, which then severed the continents apart at energetically relevant locations relevant to the flows that occurred, which are still traceable in the magnetic anomaly map. So we've gone through some oceanic plateaus. Recently I was talking about Zealandia and looking into it. So real quick, because I only got a little bit on this, but really I'm gonna focus over here in this region especially, and maybe some in the Philippines area, Philippine Sea, Philippine Plate, whatever people want to call that area, but we're starting here around Chatham Islands, and particularly in this area, which is interesting. It's got these little like doop 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 doop, almost like a saw appearance to it. Kind of going on down here too. Okay. So the Chatham Rise faults formed when Zealandia rifted from Gondwana. So notice when we look at Gondwana. Like, here's Australia. Zealandia is adjacent. There's just an ocean next to it, according to this, but the reality is South America is next to it. Like, there's an actual physical continent that applies a pressure of resistance by its being present. Like, it matters in the process, as well, especially see in Western South America, or Western Australia. But so 85 to 55 million radiometric dating. Faults formed when Zealandia rifted from Gondwana, and I kind of looked into this, like rifts, Zealandia map, maybe. In my looking for it, I couldn't really find extensive rifting in Western Zealandia. So here's Zealandia. And Chatham Rise here apparently has faults forming when Zealandia rifted from Gondwana. So faults, or faults, maybe I should, faults map, Zealandia. It's just New Zealand, mostly. Not sure. Okay. But 85 to 55 million, if you've been following my work at all, is a very important time. That's when the KT boundary passed, which is when the under pressures pushing the crust apart and etching the crust apart begin to overwhelm the crust so that it actually freely expanded to a new radius. At around the KT boundary is when that happened, when it really started to expedite, and it's sort of like which was from 541 million radiometric dating, which is not actually the age, but that's according to radiometric dating. Radiometric dating is useful for relative ages, but not absolute ages. But according to radiometric dating, the Earth's expansion process, especially with regard to this undercurrent from under Pakistan that flowed out in all directions, began at 541 radiometric dating, but it didn't really break the continents apart from a single landmass until 65 million. Like, it was beginning to rift them apart, to cut them apart, to separate them, like throughout, especially 200 million to 65, but at 65 is really when they broke apart. So that these faults formed in the 85 to 55 range. Did I say 55? If I said 55, I meant 65. 66 really, but the faults, though, 85 to 55, are like overlapping that range, so that's pretty interesting. I wrote curiously on the eastern Zealandia, like over here and not over here. I mean, I was looking at Chatham Rise video, so I didn't find an equivalent video for like this region. To really see the extent of faults. I haven't found papers on that either. So it's possible there's also equivalent or greater amounts of faulting going on the western region, but something tells me there's more faults over here on the eastern boundary, where it specifically broke away from South America and possibly Antarctica. Okay, the horns, let me just go over here. I only have 2 pictures from this. So there's the fault system. A bunch of faults. There's the islands, and this is all the oceanic plateau. Okay. There are evidences of solid basalt, volcanic like columns that then have like a cone of, I believe he said it was volcanic ash, especially around it, that was like small particles of glass that came out as like bubbles, and then the bubbles burst and became like shards of glass pretty much from these bubbles that then accumulated as this like sediment type layer atop the columns, but then erosion removed at least portions of that, so at times we can see just the basalt column that tends to be tapered at the top, emerging from the islands, which is pretty interesting. Like the pyramid, it's called. Like, maybe I can just search for it. The pyramid, Chatham Rise Islands. Image is this. Like, this is an example of one. where it's just straight basalt. But then the horn, or horns, maybe it was called. The horns, I don't know if that'll work. There we go. These ones, like that, this is the mound around it, while this is the basalt column that came up through the crust. Okay. Let's just move on from this, though. Lots of interesting things in that video. Rivers, for instance, they're in the 90 to 95 million. There are river sediments that are not marine, that are so soft you can dig them out with a spoon, were his words. Which is interesting to think about. 90 million years old, according to radiometric dating, but it's soft. I'm not, like, that doesn't even make sense to me. That it would be, like, malleable in some way as a 90 million year old, like, deposited layer. Okay, it's called the Tupwangi Formation. Is what it was called. Most limestone in Chatham rises from 55 to 35 million, with one layer from 30 to 20 million, which is the age of limestone found in mainland New Zealand. Okay, but then I ended up looking for the Exmouth Plateau. So this is where things get really interesting. Really, really interesting. Exmouth Plateau, which is really part of all of this. If we look at oceanic plateaus, one of these has Australia. Here. So I was looking into these. I don't know if I found a name for that one, but I was looking into these three that I did find a name for, and immediately it's amazing. So before we get into that, it's really important we know where we're looking at. Western Australia at one point had Sulawesi and North Maluku, these islands here, were folded inward because the earth expanded. Like, to accommodate for the expansion, it folded outward as this like tab, in part at least. And then Philippines were physically here, conjoined to Australia, like one landmass. No, it wasn't like islands like this. Like the Earth's expansion process etched the islands of Southeast Asia to be as they are today. But the Philippines were here, and then Borneo was down here, which like wrapped around the boundary of Australia. Okay. So, also, in combination with that, because the earth expanded, like there was something past the Philippines, past Sulawesi, past Borneo, and that something was North America, as well as Papua New Guinea and Solomon Islands down here, which was conjoined to Australia through these islands as a single landmass again. Although it's possible it rotated from and reattached here. I have a suspicion that it like was previously like this, like Papua New Guinea up here, like this, and then Australia rotated and rejoined through Papua New Guinea over along this path. Although, as Basil Tikoff says in this video, from Eocene I, clockwise rotation of Nick Zentner's series on Eocene, on the crazy Eocene. He mentions this is not like unequivocal. There's a lot of like debate around if this is exactly as it was. So it's possible that Papua New Guinea was just always attached over here and Australia was past it, kind of thing. Okay. Although I suspect it rotated. Okay. But it attached this way. Whether it ever detached, it was attached this way. And so Philippines, Australia was adjacent, all one continuous landmass. But in the process, a lot of currents were going through this stretch of the landmass and etching them into islands, as well as segmenting them from Australia and from North America, Laurentia and North America ultimately. And in so doing, they shaped the islands to be as they are today and segmented them into chunks that then would be put in their final resting places of where we see them today by current flows that move them. And part of the process of segmenting them was building mounds, like to segment Papua New Guinea and Australia from North America. The Ontong Java Plateau formed down here. Ontong Java Plateau, which was actually connected to the Manihiki Plateau, which was connected to the Hikarangi Plateau down here. These were all one single system before the Earth expanded. As it was expanding, it began to accumulate this mass as it like gaped the hole between South America, North America, and Australia. In the space between there, as this space opened, like a mound began to well between the pressures of the continents because they held the space as like a container, and they formed, and then they moved apart. And part of their moving apart process was that it became segmented into these chunks. And they participated in pushing them apart because this mound is forming, which is kind of like putting a hill. Like imagine there's a bunch of balls sitting next to each other, and then this mound starts to come up. At some point, the balls will roll away from one another. Maybe not balls, but even just like plates. Like if you put a bunch of metal plates down next to each other and then begin to push upward between them, at some point they start to slip downhill, and these contribute to just pushing them apart and are part of the process of the segmenting of continents. So when I realized that recently as like a fundamental aspect of how oceanic plateaus played into the Earth's expansion process, this really came back into my view. Like I've obviously, like even when I made the animation, it's obvious it was there, like this landmass. And the Philippines and this mound have some relationship. But I kind of just moved on. Like, okay, I'll get back to that someday, maybe. And I'm back to it, so that's where we're gonna go now, is to the Exmouth, I don't know if it's mouth. Let's say Exmouth Plateau, this region, which, excitingly, the Wikipedia, not all of the oceanic plateaus have like such a long Wikipedia page. But I just read it and haven't really gone into like the technical papers yet. But because it has so much like specific detail, I was like, alright, this is pretty good. I mean, it suggests that it's forming between India. So something I've noticed is like They're saying this is where India and Australia broke apart. I'm like, I don't think they were ever together. What is it? I don't know what the evidence that India and Australia were once together kind of thing is. Like, if I go to here, go to this, like, here's Australia. Notice it's up there, up at, like, Papua New Guinea's up in the pole region. This is a expanding Earth paper. So my suspicion is it kind of rotated over here and reattached as, like, the Tethys Sea opened in a intermediary step of the Earth's expansion process. So, like, it's really not, there's India over there. It's really not, like, connected at that time. Now, certainly this map is imperfect as well, but still, like, I really don't think they were ever connected. Here's the southern hemisphere, India, and then the whole length of it is pretty much East Antarctica. Like, this doesn't seem quite right, though. This doesn't seem quite right either. But besides the point, yeah, there's a suture zone. Yeah, like, this doesn't seem quite right either. Okay. So, this is in Northwest Australia, where the Philippines were attached to Australia. Mind you, another thing of note is, here's this. Philippines are above this. So I draw a current coming in this way and going into Sulawesi and North Maluku Islands region, and basically etching out this region, as well as probably depositing igneous provinces found there. I think at like 130 million and then 80 million radiometric dating. But it also, like, cuts upward between and continues. So basically, when we look at this one, it's worth being aware there's a current that's generally going up the coastline. Generally, I mean, certainly nuanced, like the San Andreas Fault is part of it, like it's an aspect of the San Andreas Fault, but it's going up the coastline, and it's going up the coastline, up this way, and then probably between here to, like, segment these two so they don't remain attached. So between Australia, which is adjacent. So, like, southwestern Australia is over here, and Western Australia, southwestern Australia. This is probably not exactly in position, but Western Australia is over here. So when we go over here, the current is going this way. So Papua New Guinea, past Papua New Guinea, past Sulawesi, and then between the Philippines and going this way, this way, this way. So it's going to be relevant as we look at the evidence to consider the possibility that this is true by looking at the evidence and seeing if it corroborates, like, a directional path and process of the separation. Like, if the first depositions are occurring down here, like, maybe it's cutting through and accumulating and then accumulating backwards to a degree, so there is some potential of that. Let's just look at the evidence. Okay. So the Argo Abyssal Plain to the north, this area right here, this Abyssal Plain, Argo Abyssal Plain, initiated at 155 million radiometric dating. The central and southern margins of the Gascoigne Abyssal Plain and the Cuvier Abyssal Plain, these regions, initiated 135 million. So first to occur was the Abyssal Plain up here, 155. So if a current is coming this way and segmenting Philippines from Australia, like, it would make sense that it first segmented the northern region. So this is good. It segments here and then it segments down here. Okay. Then it mentions Australia rotated counterclockwise to present position. So if we kind of consider that Papua New Guinea was over here, and it rotated counterclockwise so that it's this way, like, it basically, it went from an angle like this to an angle like this. So that fits. Like, it was generally more south-north than it is now. Now it's more east-west. So it rotated, although this way. According to the camera, this way. Okay, so late Triassic, which 237 to 209, high volumes of sediment accumulated off the shoreline of Australia. So in the time frame, so imagine a current's flowing and it's cutting open a gap. What's that current gonna do, especially if there's water involved? Is it gonna, like, accumulate sediments that are beginning to, like, wedge? It's kind of like the oceanic plateaus, but on a smaller scale. It's accumulating these sediments that are wedging between Philippines and Australia, but not yet, like, pushing Philippines away. So it's beginning in the 237 to 209, and then it slows down 209 to 201 radiometric dating. Then I wrote fluvio-deltaic sediments, siliclastic claystones, and sandstones. I guess that's what that's composed of. And then more marine sediments, deposits found during 209 to 201, carbonates. So more of like a elevated above the ocean floor kind of deposits prior, and then after it kind of cuts down enough, it's kind of what I'm thinking, to then begin to deposit in a marine setting. And then during the early Triassic extension initiated, or sorry, Jurassic period is 140 or 201 to 145. So during the early Jurassic, the extension of the Exmouth Plateau was initiated. Normal faults created, which are going out like this way, like parallel to the coastline kind of thing. Eastern Exmouth upper crust thinning, so thinning occurred in the upper crust here, and then Western Exmouth lower crust thinning, and it's a crystalline and lithospheric in nature, which is interesting. Lithosphere is kind of where this undercurrent is occurring. So if you imagine Philippines starts to move away, and there's this pile that's been wedging between the Philippines and Australia, but it moves away. The pile was kind of compressed, but now the pressure is no longer there. As it starts to move away, the pressure recedes. So what does the mound do? Does it stay in its present state, or does it restabilize in a new equilibrium? It restabilizes in a new equilibrium, and how it does that is just by its sheer bulk pushes down on itself pretty much, and that causes it to slide out away from Australia and create these like faults outward. So that's fitting. Continued deposition of carbonates, primarily marls. I didn't even look what marls. Earthly material rich in carbonate minerals, clays, and silt. Looks very fine-grained. Like ground up, very ground up particles. Okay, extension caused several sub-basins in the northern Carnarvon basin. So as it like slides outward, it creates these sub-basins where material can be deposited in. But particularly in the northern Carnarvon basin up here. Carnarvon. In the mid-late Jurassic, extension continued. So this extension continues through when the abyssal plains are opening. So it's kind of like Philippines are sliding away, but they're not gone. And as they move away, this extension is part of the process of them moving away. Like it's not like they're sitting there. Philippines moves, and then this bulk mass just kind of spreads out. Like as it's moving, it's opening space for this mound to like recede into. So it does it in a more continuous process with the motion away. That's kind of what I'm thinking. Which then led to magmatic intrusion from crustal thinning underplated region. So like as it's spread, underplating from this thinning led to actual intrusion of magma, which then, or intrusion of magma as it spread led to upwelling that then led to a like underplating of this whole mound to kind of create a base of this, I presume, basalt. Just says magmatic intrusion on the Wikipedia. By early Cretaceous, structural, so like 145 million, structural morphology had taken shape. So basically, by the time Philippines is like really gone, the structure of the mound stabilized. But like this is still during the Earth's expansion process, so there's still aspects to things going on. Like this is a big mound, and the Earth is expanding, and the mass itself subsequently begins to subside with like relieved pressures. So like under pressures relieve, so it subsides. So late Cretaceous to present, there is subsidence. Okay, the earliest layers, this is interesting. The earliest layers date back to 252 to 241 million, called the Locker Shale. So if we just go over here, we should probably go to this. The Locker Shale. Earliest layers date back to the Permian-Triassic extinction timeframe, or Permian-Triassic boundary, when a lot of other things are going on besides just the Siberian traps. But here's another thing going on, is this location, this wedge between the Philippines and Australia is beginning to have actual enough space open for deposition of these layers of first Locker Shale, which is the from 252 to 241 according to this. I imagine that if I go to these papers, like, these look like they're actual technical sources enough to like really confirm that this isn't just like misquoting. So it seems, even though it's Wikipedia, it seems pretty well written for a Wikipedia article, which is good, because it's just more like to the point. Okay, then the Mungaroo Formation are fluvial stream deposits, which is one of the thickest in the region from 241 to 209. Mungaroo Formation, intricate fluvial environment of meandering and braided stream deposits laid down during the pre-rift active margin of the northwestern Australian shelf. And it is one of the thickest formations in the region, 3,000 meters thick, approximately, in the distal portions of northern Carnarvon Basin furthest offshore. So, like, imagine there's this current coming in and running into resistance, and it starts going this way and wrapping around. So I'm kind of thinking it did something of that nature, where it like managed to get through to a point, and then it, like, where resistance was over here, started to deposit this layer progressively thicker further offshore. So like it's pushing outward to a maximum point that it can. And then depositing. Like a current flow is flowing, not meeting enough resistance to slow it down to then deposit. Like, it's a matter of the velocity of the current. As the velocity of the current is reduced by enough resistance, it then is able to deposit this layer. That's kind of what I was thinking of that. It's over here. The first one's, I believe, more so over here, so like that's related to getting through, but once it gets through, then it kind of wraps back around in the resistance and deposits over here more so. Okay, hopefully I can remember. This has been a couple days. All of the like details I thought were interesting. I mean, I tried to write it down, but that doesn't mean I'll remember exactly what I was thinking at the moment. So then there's the last Triassic formation from 209 to 201 called the Brigadier Formation of shallow marine claystone limestone, and it's thinner, so just less material, kind of like a hiatus that was occurring maybe in the deposition. Trying to think if there's some reason like pressure might have been re-diverted elsewhere around that time frame, like 210 to 200 radiometric dating. I don't know that much about what was going on there at that time. not here, but like globally at that time. I guess that's when, now I think about it actually, around that time, oceanic crustal age. Did you see that? This one's got the actual date. Like, this one beneficially ignores the Mediterranean, so we can kind of see 208 to 144. Like it, and I was just saying, there's a lull, a thinner deposition, formation of shallow marine claystone and limestone thinner from 209 to 201. So it's possible that all these like currents cutting between the continents actually cut between the continents, and so I'm thinking possibly with relationship to the central Atlantic magmatic province, some of the currents started to like flow atop the surface as the central Atlantic magmatic province, and the current that's flowing into Australia here is actually this current flowing this way, going over here and underneath Florida and Mexico, and then running into resistance from current going from over here eastward that's flowing under Australia and just building like a boundary, as well as pressure coming under Australia from Antarctica that's coming up this way, running into it up this way, which runs into, at that time, this way. So it might actually be that one that's most like resistant and creating this hard boundary between them. But the flow from here starts to, first of all, open the Atlantic, but also to flow atop the continents. So there's a relief in pressure. So what's going on over all the way over here? A relief in the currents, maybe, in that time frame, or particularly, at least until like the pressure builds over here to like force current through some more around 201 radiometric dating. So I would say there's some type of relationship with this one's formation extent, much thinner, only for a short time. Okay, let's keep going. Then Jurassic. So we're through the Triassic into the Jurassic, where the earliest Jurassic is called the Lower Dingo Claystone. So the Dingo Claystones. Uneven distribution. Let me see where that is from. The distribution throughout the blah 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 varies. Okay, yeah. So let's keep going. Mind you, relevant to this is the extension. So this has, again, this oceanic plateau flowed outward. Like it forms kind of smaller and then it extended outward. Due to resistance of Australia, it flowed away from Australia, extending outward and creating these basins, particularly in the northern region over here. So relevant to this is these currents fill in these basins first. Okay, so that's what we're gonna see here, is the uneven distribution of the Dingo Claystone during the Jurassic. The Lower Dingo sequence cannot be found in the Exmouth Plateau because deposition during the early and middle Jurassic was restricted to sediment filling in the empty troughs. So it slides away and then creates these troughs, these basins that then get filled by the current, which is like, if it's sort of just ocean sitting on the ocean, like it should still deposit everywhere, but because it's depositing up here, it points to a current flow from this direction flowing into them. So it flows into them, deposits the lower dingo claystone, and once it fills the lower dingo claystone, once it fills the troughs, then it's able to sweep across the totality of the oceanic plateau, which is when the upper dingo claystone begins to. So as deposition continued through the middle and late Jurassic, the troughs of subbasins filled, allowing more of the dingo sediment overflow into the distal margins of the region, i.e. the southern ones, which are the ones in the north in this direction because it was flowing this way. Although this is maybe not depicting the Australia aspect of it, but get the point hopefully if you remember those pictures. Characterizes the upper dingo claystones. Okay, so that fits. So we're get like specific details don't have to fit what I'm saying. They could be totally like irrefutably disprove the analysis, but they really shed light on the nuance instead, which is just proof positive that there is something to what I'm saying. Like, it's pretty much approaching validity in a way that modern science is not even close to. Okay. Then there's the Cretaceous. So then we enter the Cretaceous, where there are all these formations. Notice a lull in this period. Okay, but in the early Cretaceous is the Barrow group. From 145 to 139 million, major change in depositional patterns. 145, like that time frame, is commonly showing up in things like with relationship to Baja BC, which is related to what's going on over here, which if we go here, actually this one is probably more appropriate. Like, this terrain is being accreted on. This is obviously just me cutting a segment of North America and then moving it atop North America into place to be one with, and then it does not capture the nuance of the process. But the point is, these terrains are being accreted onto North America by this current going up this way, really. The current that's flowing up, cutting through the boundary, creating the western margin of North America. It's also moving materials that it's pushing into North America and accreting them. And it's kind of in that time frame when a lot of this is happening, certainly to like much more recent, like Silesia is 50 million down here. This is accreted at 50 million. But it's in that time frame. 145, like the beginning of the Cretaceous. Large uplift of Cape Range fracture zone provided sediments northward past Barrow Island. Okay, so let's look at this. At this period of time, there was a large uplift of the Cape Range fracture zone that provided sediments from the Barrow Delta prograde. So I couldn't find Cape Range fracture zone specifically, but if we just go Cape Range, like National Park. It's basically from here, and probably some type of whatever fracture zone, like generally in this region. Going north, I was thinking maybe, what I was thinking was the current that was cutting through this way was cutting through. But then at the Triassic, or at the end of the Jurassic into the Cretaceous, the current began to like get pushed inward and cut across this way, and then it like sprayed backward. So it did like an inflow and outflow and kind of looped back, as well as going over, but looping back and also going in here, I guess, like these things. So these are also evidence that a current was generally flowing along the coastline and then pushed in, but then kept going, cutting the actual coastline, but shaping the boundary along here, kind of thing. Cut in here. But especially apparent there and there, where the energy was probably most intense along the Philippines boundary. Philippines went down to around here. If we go back to this, I guess around, actually around, interestingly, just by like maintaining the size of these, Philippines generally putting it up to there made it go down to about there, which is interestingly where this is happening. So maybe there's a current coming in across this way that then like encourages current going this way to deflect inward in this location. Certainly there's more detail to this because in this map I do not include these, which are actually around, like on the sides of Philippines. Like if you imagine Philippines turned and just wedged inside here, that's more as it was with these two arms, like taken away from them. Like this indentation here is related to this indentation where it was, kind of thing. Okay, let's keep going though. How far are we? 50 minutes already? How about this? Let's just start that again. Okay, so then provide sediment northward, so this fracture zone, large uplift. So maybe it like goes underneath it too. I did not think about the uplift that much. I just wrote it down really. It's possible as it cut in here, it even went underneath it and like uplifted the region as well as going atop it, but underneath it too, and provided some uplift. I don't know the details of this uplift. Let's see. Maybe I could do that. Do that. Boyd. Hey, there's the paper. I'll have to look at this. I was hoping the map would immediately make sense. Oops. Cape Range. Oh, Cape Range fracture zone is over here. Like towards it, pointing towards it. Oh, what did I say? Uplift of the Cape Range fracture zone. Provided sediments northward. So maybe there was like a continuation where this current passed, not just here, but got past it down here. It might be beneficial to also look at this one. Where was it? At the Wallaby Plateau, which I do. Let's just get an idea of when that happened. 1:30. So the Wallaby Plateau has a 1:30 radiometric dating, kind of when it formed, time range, which is after the time period we're talking. Basically, at the time period we're talking about, a little after actually. So it seems like maybe, possibly, current was passing here, but then flowing back and just pressing into this and creating like a uplifting of this region, I guess. Maybe something of that nature. As it got down past the Philippines, especially the Philippines, like we just saw, kind of only extend about there. So the Wallaby maybe is related to Borneo more so. Like related to specifically like right here. Where this is all related to like underneath the Philippines. Okay, let's keep going. So we're almost on the Exmouth Plateau. Composed of interbedded shale. Let me read the rest of this. Provided sediments north, so this uplift of, I guess, uplift in this region provided sediments northward past Barrow Island here. This way. Although I really would say it definitely relates to this, but I'd be curious to see the details. Northward past Barrow Island and across the plateau from Barrow Delta. Barrow Delta, Australia. Geology, maybe? Not sure. Conglomerate thickness. Onshore distribution of sandstone. Notice how it goes in and like goes outward and across like a river. Like a current flow that I guess bent here. Not exactly sure what's going on there. The abrupt end of it all. Maybe even cut back down. That would be crazy. I don't see the delta location, but okay, let's keep going. Composed of interbedded shale and fluvial delta sands, caused around 135 million. And then the winning group, after forming, so the winning group, after forming, I don't know if it says it here, the abyssal, the Gascoigne abyssal plain and the Cuvier abyssal plain. Oh, there's Cape Range fractures in. Don't see the delta still. Barrow subbasin. The winning group formed after the formation of these. So after Philippines is moving away, then there's deposition of this next group. And there's an unconformity between the two. So it's almost like I was just saying, like it's bending and resistance coming back, like on while the Philippines are still there, but moving away, so they're creating like a resistance to deflect energy back, which then is bringing some currents back this way, but then it like fully gets away, and that allows for the winning formation. So if we go back here, eventually deposition of the Barrow Delta sediment ceased during like I guess 134 million, and then seafloor, this followed seafloor spreading at the Gascoigne and Cuvier abyssal plains and erosion at the surface of the Exmouth, Dampier, and Barrow subbasins, and an unconformity at the top of the early to middle Valanginian. By the late that period, through the Cretaceous, major transgression occurred with deposit of the winning group atop this unconformity. So it's almost like as Philippines moved away, they allowed for this current that was flowing through the region to actually subside into the surroundings more so, which then in a similar way to how the lower Dingo filled this region first and then went back into the upper Dingos, like covering the whole region. It went through the troughs and then it went through the whole region. It's almost like this hiatus was caused by, or maybe was caused by the Philippines moving away. And then once they moved away, like the pressure built again, and then the current could flow atop the whole of the plateau again, which then led to the deposition of the winning group. But really relevantly, the winning group, which consists of these things, which were deposited in a low energy offshore marine environment. So like it's not between two systems of the Philippines and Australia where the deposition is like squeezed, the current is squeezed. Like if we go back to the Baja BC one, this one, there's a current that's being squeezed that then really creates like a vein down the eastern Canadian Rockies area here that then cuts in against resistance, cuts in and like does all these things where it etches in and it really shapes the environment. But like it's the presence of the ocean current when it's wider, when there's a bigger space, is not really visible. Or I mean, it's certainly deducible that it was happening, but it's not something that's so clear that it's like ringing alarm bells like the Missoula flood does, for instance, the Columbian River basalt, which are actually simultaneous and involving one another and interacting with one another, albeit modern science doesn't understand that because we're stuck in like basically a framework where, sorry, I just got distracted, where radiometric dating is just held as absolutely true, and in terms of the numbers, not just the like that it can be done, but the actual numbers that we arrive at are held with like unequivocal certainty, when in the reality is there's unaccounted for variables that make like what is millions of years actually be thousands of years ago because the earth was expanding. So the winning group was in a low energy environment. That's really the key. And then that's this oceanic plateau. Like it doesn't have any other layers. because the Philippines moved away enough so that like the deposition was more balanced out, and basically the flows were more involved in just oceanic crust happening and not involved. Okay. One sec. Okay. So that's the end of this topic, and I'll just end this video here. Actually, I'm gonna go and do some stuff. I got so much to talk about. I'm glad to have gone through this. I think this evidence and probably the totality, like the more nuanced the details, the more it's gonna reaffirm and establish the precise mechanics of what happened between the Philippines and Australia. So I was just real quick. I noticed in this animation these kind of look like what's going on here. I mean, it's a little off the path. Like right there. Oh my god, let's go. Let's just real quick do this. There's this, interestingly going to there. This, and then if we follow this, it looks like it continues through there a little bit, over there, like through there. And then this one looks like it continues there. So there's a track, I guess, is what I'm getting at, that interestingly arrives at that. Let's look at the Philippines. Starting down here, there's this track that kind of diverges here, but continues here, through here, through here. Maybe this way too. That kind of goes to this front region and across, and maybe right here. Or I did that wrong, didn't I? I think I was looking over here. Did I? No. Yeah, I was, okay, yeah. I was thinking over there, but maybe this location has a close relationship to whatever this is. Almost like a hinge or a peg upon which it was connected that broke, but had these current paths. I haven't really compared Philippines to those things. I've compared them to the Juan de Fuca, like this. Here's Juan de Fuca, red line, and then just comparing it to the Philippines, where there's definitely some kind of structures like across there. Specifically, we kind of see across there, and then like over at this corner is kind of where this goes back, like the boundary, and then up to about there, and then across, and then up that way, as well as like this path right here, kind of relating to maybe there, maybe to that one that we were just looking at, some relationship between the two. But I don't think I ever noticed like this arc here. We can see it here. This arc to that corner in the western coast of Australia in this plateau region. Oh, that's just real quick. Let's make sure I wasn't muted. Well, so I want to do it this way. Here. Like so. Yeah, I'm still looking at shallograms. They're still amazing. Create new. Do that. And then without changing the zoom, just kind of grab the Philippines. I guess turn it this way first. Grab that over here. Real quick, lasso the Philippines, like so. Oops. Can probably kind of ignore this portion, but so let's just do it right there. Like I said, that was arms that were actually from the sides. Not sure the exact boundaries. Obviously, I just cut across a landmass, but I'm just trying to get this done real quick. Let's say 10 degrees, maybe. Degrees, maybe. I like. If I hinge that little point on there. I'm not sure this fit the same way as it was. Like, I'm pretty sure it was all the way up there. I don't want to change its size. Like, maybe it slid though. Like if it started here and then went like kind of that way as it opened. And then maybe they ended up hinged over there, like there. I'm really confused why it's not fitting the same as this. Did I cut some off? I don't think I changed the size. Let's see. Let's just measure from like here to here. 963. And then assume it starts about there. So 963. How far do we go from there to there? About. So I was pretty much interpreting that Sulawesi one was folded to about there. And then the Philippines were adjacent. And then that. It does have like a track. Maybe it literally is like a track, like a railroad track, like it slid a little bit over. And even though it was over here, it like pushed over to about there. Okay. Definitely some looking into it to really get precision, but that's too bad. Nothing just immediately lines up. It definitely looks like there's a track here and one next to it. So the fact that there's like two adjacent to at least here, and then some stuff going on back there that bends. Maybe something there too. It does have similarities to Philippines. Alright. Thanks for watching. See you next time. Peace out.